My name is Dr. B.L. Narasaya. I retired from Geological Survey of India as Deputy Director General. It is an earth science organization encompassing all the investigations pertaining to the earth and in various spheres of geoscientific mapping, mineral research, environmental geology, and lot of many other related subjects, including medical aspects and medical geology. With such a broad comprehension, I have developed an interest towards society, towards education, towards educating our youth and disseminating the knowledge available to the concerned target population. In this connection, this is another message concerning the most important environmental and other scientific aspects regarding a fundamental attribute which the world discovered as radioactivity. This is the title. So the title of the project is Radioactivity, Science Developments and Futuristic Outlook. Well known to the world and much more to the physicists and chemists and related scientists, it is a fact that there are only two physical entities, matter and energy. Using determinative laws, they started proving and probing into the underlying order of these physical phenomena. Chemical laws pertaining to elements had been elucidated. The Newtonian mechanics pertaining to the macro universe laid its clear foundations. Gravity, magnetism, electricity were evaluated. The quantum mechanics subsequently unraveled the micro world. The smallest is fully understood. The convertibility to equivalence and relationships between matter and energy, wave particle duality, etc., occupied a prime theme in the conceptual understanding. Maxwell's electromagnetic revelation was a landmark. Investigators probed the phenomena of electron, cathode rays, X-rays, and also the radioactivity. These are all interrelated. Subsequent to radioactivity and further probes, Madame Curie, a pioneering physicist and the only luminary at that time who braved the otherwise difficult society, including academic elite, got also the first doctorate degree from the University of Paris in physics. She worked on pitchblende, the main ore of uranium, and carried headloads and tons of material extracted from the Joyas-Timsal mine in Czechoslovakia. She did further pioneering work and processing work of separation of elements like radium. This is a dedication to her memory and to her outstanding contributions. Further, respectful tribute is to all and many investigators in the field. Only some salients are taken here for this purpose. Science led in a way. The modern world, so to say, the present day world, 21st century civilization, could be considered to be enjoying not only the fruits of modern science developments and the benefit of technical devices, but also we should be equally aware of the possible other side of these developments as well. It is time to recapitulate the people behind the inventions and the discoveries made, and also some of the workable events that those yesteryears, and to some extent to have a healthy mind and a thinking for the welfare of humanity on a global perspective. Eminent natural philosophers all over the world started pondering over the primordial forces of nature: air, water, earth, fire and sky, the Panchabhutas from India, from their respective perspectives. Philosophers from India described in their references Anu and Paramanu, and also in many ancient scriptures. Greeks also investigated. In Greek words, atomos means uncuttable. Many Western thinkers further brought out rigorous and empirical laws pertaining to matter and also the elements, and even went into the extent of organizing the then known elements into an order, orderliness, or a framework. Many were in this direction. This is a frontier of matter in general. Remarkable it was in the year 1869, a Russian scientist Dmitry Mendeleev came out with a table showing the formatting of the elements into rows and columns based on rules of two analytical parameters, the atomic weight and valency. Mendeleev then organized about 60 or odd elements then known and even left gaps for future elements to be discovered, either to unknown. These prospective elements were studied with a predicted parameters and their awaited new discoveries. These elements were later discovered as scandium, gallium and germanium, following magnesium, aluminum and silicon. Curious to know is the fact that by 1869, Mendeleev's first table, elements thorium and uranium were also known. Martin Klaproth discovered uranium in the 18th century. Their chemical properties were known. Uranium salts were used for other purposes, maybe like painting and others, and people faced the dire consequences of the not unknown property of radioactivity of uranium and its compounds. 19th century development of the first periodic table and the basic tenets, the atomic weight and valency on which the foundations were laid, these are fully borne out by later nuclear and electron structure investigations, and the atomic number and the outer shell configuration of electrons closely mirror atomic weight and valency. Mendeleev, however, was skeptical of the nature of the electron, but this was later discovered in 1896 or 97 by J.J. Thomson. In the 21st century only, the formatting and the progress of the elements of the periodic table with newer discoveries closed in with atomic number 118. This is finally completed. Further work is still in progress. Uranium has atomic weight of 92 and thorium 90. Beyond 90, all are radioactive. Conspicuously, the numbers are atomic numbers are number of protons in the structure as discovered by Moseley. There are two elements, technetium-43 and promethium 61 are missing on Earth. They were made in 1937 and 45, respectively in advanced nuclear facilities, etc. The bottom rows of the periodic table, 58 to 71, lanthanide series, and 90 to 102, actinide series, are important elements of the rare earth group and the actinium group. Most of the elements in the actinide series are synthetic only and radioactive. Some of them find applications in nuclear industry. The Nobel Prize for Chemistry in 1911 went to Rutherford for chemistry. He discovered that the atom had a nucleus. The particle at the nucleus was proton, positively charged, and where the mass is entirely concentrated. By that time, electron was already discovered. Later, in 1932, Chadwick discovered neutron, particle of the same mass as proton, but no charge. And neutrons are in the nucleus, contributing to the mass, and various isotopes of different mass variants are thus existing. Isotopes belonging to the same element and have different masses. Many elements are stable and some are unstable. 20th century discoveries thus led to the full elucidation of the atomic structure, the subparticles, neutron and proton making up the nucleus, where the entire mass and positive charge are concentrated and the electrons corresponding to the number of protons are in the orbital shells. Quantum understanding and the elucidation of the energy distribution patterns, the special signatures completed the nuclear scenario. A is the mass number, Z is the proton, is the atomic number. These define particular atomic species or nuclides. Masses of nuclides are measured in terms of atomic mass units. Atomic weight is computed taking into consideration relative distribution of its different isotopes. There is a difference between the nuclide mass and the atomic mass. This has further significance in the energy scenario. The last column of the elements, the zero column of the periodic table, and the entry of the noble gases, it is a culmination of the periodic table. The discovery and entry of noble gases and their placements at the end are the culmination of the periodic table in terms of the electron structure and stability. This is a remarkable breakthrough. Noble gases are stable and do not enter chemical reactions. Their electronic structure is also stable and completes the end of each row. The first noble gas, helium, protons 2, atomic number 2 and mass number 4, helium 4-2, was discovered first from the Sun by a British astronomer Johnson and India from a study of the corona of the Sun on a full solar eclipse day. Spectroscopically, helium line was detected. Mendeleev's first table does not report any noble gas. Later, to helium it is further reported from earthbound materials. The other noble gases are helium, neon, argon, krypton, xenon, and radon. Below radon, end of the seventh period, is the last discovered new element 118, which is also synthetic. There are many investigators associated with the discovery of noble gases, led by William Ramsay and so many people. Lockyer was also there, Hillenbrand and many others, Sir William Crookes. They were pioneering investigators in many related fields. Helium was also identified in their experiments on heating uranium ores by Hillenbrand. Some of the noble gases find place as disintegration products. Helium is a stable nucleus and there are various isotopes of helium. Beams at the end of 19th century. In 1895, Rontgen found that a cathode ray tube gave off rays that made a phosphorescent screen glow. Rontgen's mysterious rays are called X-rays. They also made a glass glow with a fluorescent light. In 1896, Henry Becquerel found mysterious rays emanating from uranium ores. Becquerel wondered whether naturally occurring fluorescent or phosphorescent materials might also emit X-rays. Uranium salts were known to be phosphorescent. In the same year, he reported his observation that potassium salts, potassium uranyl sulfate, K2UO2 2H2O, SO4 twice 2H2O, could expose a photographic plate even in the dark. This is a remarkable observation. Here, fluorescent substances are considered to be those which emit light when light of a different wavelength is shone on them. These phosphorescent materials do go on emitting light even after illumination is removed. Becquerel knew that uranium salt glow was stimulated by sunlight, yet he found that photographic plate was affected due to uranium compounds which emitted yet another radiation not related to the fluorescence. Curie called Becquerel's radiation radioactivity. It is found to be the first element to be radioactive, and then thorium. There are many other radioactive elements. Natural uranium ore contained other radioactive elements also as traces. Becquerel and Curie together shared until not the Nobel Prize for radioactivity. Curie's further investigation found that polonium is 60 times more radioactive and radium is 400 times more radioactive than uranium. Madame Curie got her second Nobel Prize for discovery of radium. Maxwell was a pioneering scientist in proposing oscillating wave and electromagnetic nature of light. Rontgen's X-rays have penetrating power. They are electromagnetic waves of very short wavelength. Max Planck in 1900 proposed that an atom of matter in contact with light can increase or decrease its energy in multiples of an indivisible unit of energy. Einstein took this logically and argued that light itself exists in such indivisible units called quanta or photons, the elementary particles. Einstein's Nobel Prize was for photoelectric effect. J.J. Thomson already proposed an electron. Planck's energy does not exist as a continuous stream. The smallest amount of that can be no further divided. Light is an energy and also heat. Around 1908, Curie discovered that atoms of new element radium continuously hurled out tiny pieces of itself, thus losing weight in the process. Unity gave rise to complexity. Energy released in radioactivity, etc., called for an explanation. Later detailed studies provided explanations of the electronic structure of elements, the atomic spectra, and the quantum dynamics. The atomic structure, the quantum details, and the order of the elements unraveled fully after centuries of interconnected multidisciplinary investigation. Thus, some nuclei already at very low energies are stable. Others with different arrangement of neutrons and protons tend to lower their energy by emitting different rays, alpha and beta. These are radioactive nuclei. Radioactive atoms like uranium and thorium thus are unstable. Their nuclei spontaneously disintegrate. One of the products of disintegration is a massive positively charged alpha particle. Rutherford used alpha particle as projectiles, firing them at atoms and observing how they scattered. Beta particle emission is caused by decay of a neutron into a proton and an electron. That the 20th century paved the way for a knowledge of the structure of the atom, the nuclear atom, and the ordering of the elements. Some nuclei experience complex computation of forces when subatomic particles and the relative distribution of mass due to neutrons n and p and its ratio. Three types of reactions are nuclear. These involve changes in the matter and emissions of radiation when the nuclei change spontaneously. They emit radiation and these characterize radioactivity by and large. Only the number of protons defines the atomic number. There are definitive laws governing nuclear processes such as disintegration by laws of probability. Chemical Rutherford found out the exponential equation of decay. Half-life is the time required whereby half of the parent nuclide undergoes disintegration. Rate of decay is a constant for each nuclide process changes which happens in discrete stages. In the radioactive decay series, uranium creates many newly highly radioactive isotopes, radon, polonium, and finally lead. When uranium is bombarded by neutrons, barium, atomic number 56, and the krypton are also found. Uranium has different isotopes, 235, 238, etc. Uranium-238 is the most abundant naturally occurring one. In 1907, Boltwood found out that lead was the final product. Campbell and Boltwood found out that potassium and rubidium are also weakly radioactive. Radioactive decay series. This emits three types of radiation, alpha, beta, and gamma. Alpha is a particle with two protons and two neutrons, the nucleus of a helium atom. When alpha particle is emitted from an atom, the atom undergoes transformation to another atom with atomic number lesser by 2 and 4 lesser in mass number. Beta is emission of a negative electron, atomic number increases by 1 and mass remains as same. Gamma is an energy packet. In addition to natural radioactivity, there is artificial radioactivity. Irene Curie and Joliet carried out artificial radioactivity experiments. Newer elements are created for research and other purposes. Nuclear fission and chain reactions. A parent radioactive nuclide, when bombarded by neutrons, releases its daughter products with further release of neutrons participating in a number of reactions. The reaction goes on as a chain. Under controlled conditions, nuclear reactors are employed for production of electricity energy. This is briefly the principle. Suitable fissionable materials, control rods, moderators, coolants, etc. are also part of the vital assembly in a nuclear assembly production. Moderators reduce neutron energies, control rods reduce rate of fission, coolants in different types of reactors are H2O, D2O air, etc. Uranium-238 isotope is the most dominant one. This does not undergo fission. Uranium-235, a very much less available isotope, is fissionable. Breeder reactors convert the more abundant uranium-238 into more useful fissionable plutonium-239, useful for energy purposes and other needs. Also, fissionable U-33 is from uranium to thorium-232. Plutonium-239 serves as an alternative for uranium-235. The present-day world is well aware of the applications of modern science, such as the spin-offs of the processes of radioactive materials and their properties. Radiotherapy is also one. As a cure for cancer, spread of cancer cells is called metastasis. There are many other radionuclides, such as iodine-131 for thyroid, and isotopes of other elements are also in use in application for varied medical treatments. There are some modern devices like PET, NMR, CAT scan, MRI, pacemakers, titanium implants for bones, all newer developments helping the humanity. X-ray diffraction was used for DNA and hemoglobin structures. Many countries, for meeting their energy needs, either due to shortages of fossil fuels or renewable resources, depend upon nuclear energy by fission by reactors. US, UK, France, Japan, etc. were among the developed countries. India was on its phased program for harnessing nuclear energy by establishing nuclear reactors for the overall country's needs, both civilian and also otherwise. The astonishing phenomena is fusion and fission. Enrico Fermi and used neutrons to bombard uranium atom. Bohr recognized that uranium-235 is more feasible for fission. In 1936 itself, Bohr recognized that nucleus breakup as a tearing of water drop. On the other hand, nucleosynthesis by fusion process was recognized in stars by Hans Bethe. Fusion experiments are also going on. The world was aware of the usefulness of the atomic fission, and the bombs thereupon were also used for definitive purposes. Hiroshima and Nagasaki were examples in the year 1945. Modern nations, civilizations in their defense needs could devise their own policies, but as even a nuclear testing would cause environmental degradation by way of new radioactive isotopes entering the atmosphere, soils and waters, there is an emphasis on environmental engineering and the safety of the humanity. The world should remain a free place for all civilizations and nations to thrive for betterment of humanity. Vasudhaika Kutumbi, like any other property, its magnetism, etc., is an ubiquitous property. Earth's materials contain radioactivity, and materials are radioactive. There are many radioactive isotopes. Each cell of our human body contains radioactive atoms. Minute traces of man-made radioactivity is also all around. Many common and stable known elements like carbon and potassium have the radioactive isotopes. These are used for definite scientific and medical purposes. Among naturally occurring materials, uranium is highly radioactive. Among the elements made in nuclear reactors, plutonium is highly radioactive. There exist radioactive isotopes in human body, some through our food, and some are due to other extraneous experiments like environmental testing, nuclear testing, and nuclear accidents even. The epilogue. Earth is a tiny blue fragile planet with blue skies, flowing water, and the bliss of life. Survival is dependent upon energy. In future, energy crisis deepens. Global issues like climate change and carbon emissions vis-a-vis greenhouse gases further need a global attention. Fossil fuels are one day exhaustible. The future has to look for greener economy, hydrogen economy, and only alternative research and other energy resources from alternative sources, renewables, non-renewables, despite uneven distribution of natural resources. A global networking for supply to demand will relieve the problem. For example, tropical countries have such solar energy potential. Oceans, wind, biomass, etc. have all to be tapped. nuclear energy under the best possible experimental and controlled conditions for many countries is one of the safest routes, and probably environmentally also it does not cause degradation. Let us protect our mother planet Earth and hope for the survival of the living organisms and the planet Earth. Earth to be protected must be conserved.